Hello everybody. Today we're going to find out how to get the electric field at some point P, a certain distance A, away from an infinite line charge. The charge of this line is called lambda, which is charge density, charge per unit length, units coulomb per meter. So the first thing you need to do is find a small little segment. I will just put it right here, small little segment of the infinite line, which is a distance x, and this x is a variable as it can fluctuate. It can go from here to here, from here to here, from here to all the way to infinity, from here to all the way to negative infinity. Therefore, right now I'm just drawing it as here, and then this little segment has distance dx. So the amount of charge residing in that little segment is going to be a very small amount of charge, dq. And what is dq? Therefore, dq is dx times charge density, which was lambda. Therefore, dq is lambda dx. Now we have to draw a distance from that little segment to point P. Let's name it R. As you can see, we can calculate R by Pythagorean theory. This side is x, that side is a. Therefore, R equals square. Well, I'm going to over here so we can have space there for the angle later. Down here. R equals square root of x squared plus a squared. Now, we want to find the electric field. That's right. So at point P, if this is the dq, where would the electric field point at? And right now it's not E, it's dE, because it's of all, to find E, it will be of all, the sum of all of the infinite little tiny dq's. Therefore here, since the charge is positive, it will go away from it. And since down here is not directly to the side, it will go at an angle. So this is dE. And as we've seen before, every vector has x and y components. Therefore, over here it will be dex, and up here it will be dey. But as you said, we want electric field, which is of all the sum. So let's just remember we write another x because x will fluctuate. Let's just say we have the other dq over here, and they're infinite dq's. If they will, in this by symmetry, if they will be by here, the dE will go like that. Dey will go down, and dex will go that way. So for every negative x, there's going to be a positive x distance, because it goes all the way from negative infinity to positive infinity. So as you can see, for everyone here, you'll have one here, so you'll have a component there, component there, component there, component there. So as you can see, every component, y component of all the electric fields will cancel, and then you just have the x components. So how do we get all of them? We sum them all, and there's infinite sum. Therefore, we take an integral. So first, what's dE? dE equals k dq over r squared. We already figured out dq, that's lambda dx. Lambda dx, and r squared will just be this squared, therefore x squared plus a squared. But dex is not the same as dE. We have this angle, which is the same as this angle. So dex equals dE, and DEX is the adjacent side of the angle, therefore will be cosine of theta. And we can also calculate cosine of theta. Cosine of theta equals adjacent side, this side where the DEX is, and that is A, over hypotenuse, R. We also already calculated R, so cosine of theta is A over x squared plus a squared square root. Therefore, DEX equals DE A. We already know DE as well from up here. Therefore, DEX equals K lambda dx x squared plus a squared times cosine of angle, which is this, A over x squared plus a squared square root. That's DEX. And we want to find EX, which is the integral of all of that. So now we're going to set up the integral. EX equals integral from negative infinity to positive infinity of DEX. Therefore, K lambda dx. As you can see, these are the same things. So, I'm sorry, I couldn't see a bit, but so this is like when you have b times square root of b. That's so b to the 1/2 times b. So b to the 2 halves plus 1/2 b to the 3/2. Therefore, when we plug it back in here, well, that will be b, which is x squared plus a squared, all of that to the 3/2. And we have the extra a from up here. So that's the integral. So the integral is of dx. Therefore, all we care about is the x. Everything else are constants in this integral, constants. So we can take them out. So EX equals K lambda A integral of x squared plus a squared to 3/2 dx, negative infinity to infinity. Now, as you can see, this is a very complex integral. You will have to use trigonometric substitutions, trigonometric identities, inverse trigonometric functions, and I think we'll go over that later, or you can solve it. But basically, the point of this is to show you that to get all the way here and to solve this integral, it will be very complex. And that's why Gauss's law is really important, because from Gauss's law we can solve this much faster, much easier.